evening. We begin the lecture for today. Little bit of explanation on the numbering scheme. Last lecture was unplanned review lecture, so we called it 21. So this is actually the lecture 21, which follows lecture 20. So again, it's called lecture 21B because there's already another lecture 21. But this is the continuation from where we left off in lecture 20. Did get some feedback from students saying that some of the material covered in lecture 20, that was Wednesday of last week, was not very familiar to them. Again, my request to you is, if something is not familiar to you or is material that you have not seen before, please do indicate, and then we can slow down. I had assumed that most students would be familiar with the concepts of differential modulation, differential detection. But let us look at it. We'll pick it up from there and continue the discussion. So today's lecture will start by a quick review of what we had seen in the last class. Some interesting observations about the fading channel, which again, as I mentioned, is very important that you have an intuitive feel for the aspects of fading. And once we understand that, we'll go back to asking the obvious question. We have coherent modulation, coherent detection. You have differential modulation, differential detection. What about the cross combinations? Does it make sense? Are there scenarios in which you would want to do it? And if yes or no, what are some of the pluses and minuses? We'll take a quick look at it. The purpose of today's lecture is to set the formulation for deriving the analytical expressions for BER. Again, I'm assuming that the derivation of analytical expressions for BER in AWGN is familiar to you from digital communications. So what we are going to be looking at is the aspect that we are looking at the formulation in a fading channel. And so far we have looked at fading channels which have the Rayleigh statistics. So we begin by looking at a Rayleigh fading channel. So we will look at the two of the most simple forms of modulation, saying that once we understand this, it can be easily extended to other types of modulation which belong to this family. So we will look at the differential BPSK and BPSK and look at some higher SNR approximations. But first, let's quickly summarize what is our material covered in lecture 20. So coherent detection. If we assume that we will use the sample notation, so coherent detection says at the kth time instant, my received signal is a function of alpha k e power j phi k, that's my fading coefficient, times the transmitted symbol sk plus eta k, the AWGN sample. And as we discussed in the last class, we do need to have two steps. One is where we estimate the channel estimation. I need to know what is alpha k e power j phi k, channel estimation. And once we have done the channel estimation, we can then do the data detection. So the estimates are always denoted with a hat, e power j phi k hat. So that means through some process using training symbols, I have obtained an estimation of the channel. And once we have obtained the estimate of the channel, then we can do the data estimation. Data estimation, that would be getting an estimate of sk hat. And we also said that you can go back and forth between these two methods, that you can do sk and then get the estimate of the channel at the next time instant and then go back and forth. That would constitute data driven or data directed or decision directed. Based on current decisions, you are doing channel tracking. Decision directed channel tracking, and we also indicated that this is the one that makes it vulnerable if you have errors creeping in either in your estimation or in your tracking. It can lead to cascading effects, and therefore we wanted to make sure. So just to remind you, the coherent detection structure is that we will have training sequences which are known symbols that are transmitted, followed by segments where there is unknown or user data that is transmitted. Using the training sequence period, we will estimate the channel. And using those channel estimates, we will then detect the data. However, if the channel is changing, then we must do continuous tracking of the channel even between these two training bursts. So that's the mechanism that we have. So let's summarize our understanding so far that, that we have coherent detection. That is our is a method that we are most familiar with, and some of the challenges that we will face in the use of coherent detection in a fading channel is the ability to estimate the channel and also to do error-free or as close to error-free channel tracking so that we can continue to make the estimates. So what are some of the observations that we have made? That if there is a fade, then what happens is during and after a fade, because that's when my estimation and detection process can go wrong. This could lead to errors in likelihood of errors in demodulation. Likelihood of errors. And keeping in mind that fades can occur, even if my average SNR is quite high, the instantaneous SNR can fluctuate. So this can cause me errors to occur just suddenly because of the presence of a fade. And we have also discussed that some ways by which we will mitigate. And some of the ways that we would mitigate fading, the errors caused by fading are, what are some of the ways that we have discussed? Error corrections, okay. One would be FEC, that's a very powerful method. We have several powerful techniques for doing the error correction. Second one? Hopping is definitely one way of doing it, yes. Changing your sequence, but then it must be either you must repeat the data, because if you have already lost the data due to a fade, you must do some combination of that. If you do, which means that in hopping, let's say you do a repetition of data, you are losing a lot of overhead. A way by which we can avoid that overhead is by antenna diversity. And we will actually devote a substantial portion of the course to understanding antenna diversity, because antenna diversity basically says that I have multiple antennas, and if one of the antennas is seeing a signal which is affected by a fade, hopefully the others are not, and pick the antenna or combine the antennas to get a better improvement. Now I want to go back to block diagram, which helps us understand the property of bit error, the bit errors that happen in fading channels. Okay, so what we said was between data and modulation. Between data and modulation, we would like to insert an FEC, because that is what will make our system robust against those sudden dips in the signal to noise ratio. The question is, now do I connect like this? Is it this connection, or is there something else in between? Anything that you have come across? Source and channel coding. So I'm assuming source coding has been done. You have compressed your source, and whatever is the information that you want to transmit over the channel, that you have protected using a channel code. Okay. There is a very important block, interleaver. So there is a block which has a very important function, interleaver, in the context of a fading channel, and let me just take a moment to explain. Again, keeping in mind that we are building our comprehensive understanding of fading channels, and the aspects of interleaving will be studied in the context of error correction codes, but very important for us to understand intuitively what it is. So let's take a look at a very simple interleaver. It's called a rectangular interleaver, wherein you write the data in one way and then you read out the data in another way. That means the data that is coming out of your FEC is coming out in the following sequence: 1, 2, 3, 4, all the way up to 25. Let's say we have 25 bits to be transmitted. I've written it in the form of a square interleaver. I've written the data in a vertical form: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I'm going to read it out in the horizontal form and transmit it in that direction. This is the transmit direction. This is so the data will be transmitted not in the sequence in which it was generated, but it will be transmitted as bit number 1, bit number 6, bit number 11, and so on and so forth. So that's the nature of it. So this is the data sequence that is being transmitted. Let us say that a fade occurred and affected 3 symbols. So 16, 21 and 2 got affected in the process of a fading, the fading process. So in order for my FEC to work, let us see if this interleaver actually made any difference. So when the data is fed back into the decoder, which are the bits that are in wrong? Basically, you have to, the sequence in which it was generated, that's the same sequence in which you have to give it back to the decoder. Encoding, decoding has to be in the same sequence. But it got transmitted over the channel in some scrambled form. So if you look at this sequence, bit number 2 was in error, bit number 16 was in error, bit number 21 was in error. So it looks like they were scattered about, and it looks like the positions are random. Okay. So here is the observations regarding the interleaver. Why we want to use an interleaver? Not so much because we want to understand interleavers, but because we want to understand the pattern of errors that happen in a fading channel. So typically in a fading channel, you will get consecutive errors, because when the channel goes into a fade, it's likely to affect multiple symbols. So consecutive errors are likely to happen in a fading channel caused by fading. Okay, so this is something that we recognize. So therefore, now another important element which you may have already studied is that most of the error correcting codes work best if the errors are random, work best with random errors. So string errors or a chain of errors generally actually can cause a failure of the error correction mechanism, work best with random errors. So FEC is our technique to work against fading, but FEC works well with random errors, does not map with what happens in a fading channel, because what will happen is exactly like what we see here, consecutive channels. So this basically tells us that the interleaver plays a very important role, and that interleaver's role is to make the consecutive errors look random. Interleaver, the job is to make the errors appear random. Okay, we cannot change the fading, but you can, when it comes as far as when the decoder sees, it looks like, okay, some random 3 errors are and the code might actually be effective. So errors appear random because of the presence of the interleaver and the deinterleaver on the other end. The pattern looks. So what do we want to take away from here? Errors will occur as bursts in a fading channel. Okay, so that is why coherent detection has its limitations, because if I have consecutive errors, then my likelihood of me losing track of the channel is high, and once I lose track of the channel, then I will have performance degradation in my errors. Okay, so now let me move into the effect of interleaver. We have already said it will make the consecutive errors appear random. Okay, the 2 questions that we wanted to look at: coherent and differential. Cross combinations. Coherent modulation with coherent detection, differential modulation with differential detection have already been studied. Now let's look at the cross combinations. And again, this is more for us to make sure that we have a good handle on the fading channel and our ability to work with this type of environment. Okay, so differential modulation basically says that my current symbol that I want to transmit, let me call that as theta k, is given by theta k minus 1 plus delta theta k. The information is contained in the delta theta k, and delta theta k is determined by the bits that I want to transmit. If I take a QPSK constellation, a 4-level constellation, there will be 2 bits deciding delta theta k. Let me call that as bk0, bk1, and of course if it is a higher level, you would have more bits that are determining that. So given this scenario, basically the coherent detection mechanism says what's the received symbol at time instant k. At time instant k, it's a complex scale factor, and I can write as alpha e power j5. I'm just writing it as jk for simplicity. E power j theta k plus eta k. That's my received symbol at time instant n. What does coherent detection do? Coherent detection says, I will tell you what zk is, you tell me what theta k is. Okay? So, the coherent detection mechanism will help me get an estimate of theta k at the time instant k. Now, at the time instant k minus 1, it is zk minus 1 e power j theta k minus 1 plus eta k minus 1. That is the equation for the received symbol at time k minus 1. Basically, this link is coherent detection, because that is what we are coherent detection. Coherent detection, and let me write down this would have given me an estimate of theta k minus 1 hat, let me call that, I would have through the process of coherent detection. Now, because I have done differential modulation, I need to combine these two pieces of information to get delta theta k hat, which will be theta k hat minus theta k minus 1 hat. So, there is absolutely no problem. If you have encoded the information in a differential form, I can do coherent detection by detecting the received phases at each instant of time and then taking the phase difference, because that will tell me what is the differential phase between the two instances of time. Okay. Now, here comes a very important element. When everything is error free, no problem, things are going fine. But what happens if theta k is wrong? If delta theta k or if theta k hat is wrong, that means the coherent detection process because of noise made an error there. Okay, what is going to happen? It is first going to affect BK0 and BK1. These are going to get affected. These will be affected. Why? Because delta theta k is wrong means theta k is wrong is delta theta k will be wrong, and therefore these two will be affected. Okay, not a problem. Whenever you make a wrong decision, it is going to affect the information bits that you transmitted. However, notice that the next symbol delta theta k plus 1, delta theta k plus 1 also depends on theta k, because that is theta k plus 1 minus theta k hat. So, it is going to affect. So, which means that bk plus 1 comma 0 hat, bk plus 1 comma 0 hat are also affected. That means one wrong decision is going to make wrong decisions, make errors occur over two symbol durations, which were actually information transmitted. Okay. Now, that is an undesirable effect, because coherent detection, what does it do? If I make a mistake in my current decision, it is going to affect only my current bit, it is not going to affect future or past bits. So, keep in mind that if I try to do this method, differential modulation, and I do not do differential detection but I do coherent detection, then the penalty that I pay, or the consequence is that one decision error affects multiple symbols, okay, affects at least two symbols. That is an undesirable property, and we probably do not want to use that, and therefore this combination is not a very commonly encountered one. Okay. Now, let us look at the second combination, where I do coherent modulation and I want to do differential detection. Let us quickly look at this combination as well. So, this combination says that the received symbol at time k minus 1 will be zk minus 1, the fading channel, e power j theta k minus 1 plus eta k minus 1. Rk would be zk e power j theta k plus eta k. Now, since it is coherent modulation, let's make sure that we are clear. Theta k minus 1 is determined by directly, not through a differential phase, is determined by bk minus 1 comma 0 and bk minus 1 comma 1. So directly it maps to the transmitted phase. So the differential detection mechanism says RK minus 1. I make the assumption that ZK is approximately equal to ZK minus 1, and then I will do the following operation where it says I will do RK minus 1 conjugate. That is the differential detection operation, again exactly like before. This will eventually get for me the metric e power j theta k minus theta k minus 1. Okay, this is what I will get through the process of differential detection. Now what am I and so basically this effectively tells me what is delta theta k, but delta theta k is not what I am interested in. I am interested in theta k. So theta k estimate will be theta k minus 1 hat estimate plus delta theta k. So you in order for you to get the information that you want, that you actually transmitted, which was delta theta k, you would have to get theta k minus 1 and then add to it the differential phase that you obtained through the differential detection operation. Is that clear? Basically you have done differential detection. Differential detection will give you the phase difference between the two symbols that you are which you are using in the differential detection operation, that is delta theta k, and this is what is so now comes the important question, where can I make a mistake? In differential detection I can make a mistake in the estimation of delta theta k. So if delta theta k is wrong, okay, then definitely theta k hat is going to be wrong. Even if theta k was correct, if this is wrong, theta k is going to be wrong. What about theta k plus 1? Theta k plus 1 is wrong. Can you tell me about theta k plus 2? Is also wrong. Why? Because you're driving a reference, wrong reference. Your reference got affected, and therefore even if you're making correct decisions on the delta thetas, when it maps to theta k's, it's actually wrong. So this coherent modulation differential detection has catastrophic error propagation. So this is a very dangerous one. Definitely you don't want to try this. Though it looks like you can do detection without doing channel estimation, this is not a good way because there is error propagation. And it's good for us to know some of these just at an intuitive level, because these are the things that help us understand a big picture of about the differential detection. Okay, any questions about the two cases that we have looked at? One with differential modulation and coherent detection. The other one is coherent modulation and differential detection. Both of them do not give us an advantage. If you're doing coherent detection, best is to go for coherent modulation. If you're doing differential detection, do it with differential modulation. That's the right way to do it, because you intend it at the transmitter, you undo it at the receiver and get the information that is needed. Any questions? The question is, how do I start the decision process? So you always assume, if you remember, we transmitted a set of known symbols. So you assume that a few symbols are known in the training sequence. So you can use the last symbol of the training sequence as your starting point, because that theta k is known to you ahead of time, and from there on you do the differential modulation. Okay, so yes, unless somebody told you what was the starting point for the theta k's, you cannot really start your detection process. That's a good point. So maybe to summarize, when would I use differential detection? And along with differential modulation, definitely I'm not going to use it separately. So the question would be is, when would you use differential detection with differential modulation? Differential detect with differential modulation. Okay, that's the, when would I use that? When would you use that? When, first of all, basically you must make sure there's no multipath, because otherwise differential detection will fail. So I must have frequency flat channel. Frequency flat channel, that means there is only one channel coefficient, okay, Zk, that I need to estimate at every given instant of time. Now that happens to be a very easy problem for coherent detection. So obviously if you assume frequency flat channel, then coherent detection would be the obvious choice, right? Because one channel to estimate, you can track it. But would there be any condition under which you would prefer differential modulation? Any condition under which you would prefer differential modulation? High Doppler, because that is when the tracking of the channel may becomes difficult. So flat fading and the presence of high Doppler, fading with high Doppler, under this condition you may be better off with differential detection. So basically when channel tracking becomes unreliable, when channel tracking is error prone or unreliable, then under these two conditions, then differential detection with differential modulation would be a preferred choice, because you may do better than the coherent case. Okay, so that is just a piece of information that's to help you piece together the complete understanding of the fading channels that we are working with. Okay, we move on. So the heart of today's lecture is our goal to obtain analytical expressions for BER in Rayleigh fading. Now BER is always connected to SNR, signal to noise ratio. Now in the context of an AWGN channel, the signal to noise ratio is EB by N naught, and it is a constant. Now the difference comes when we work with fading channels, because there is no notion of a constant SNR, because your signal is fluctuating, because the SNR that you have is actually alpha squared EB by N naught. EB by N naught is a constant, but alpha squared is a random variable. Alpha is a random variable, so alpha squared is also a random variable. So therefore this is not a constant, this is a random variable. And so we don't call it as a single number SNR, we just don't call it SNR, we call it as instantaneous SNR. What is the current channel conditions, which depends on alpha, and that will affect my SNR, so there is an instantaneous SNR. Now this also tells us that if it's a random variable, I can meaningfully talk about the expected value. So the average value of the instantaneous SNR will be expected. So if I denote this by gamma, then average value of the SNR is expected value of gamma, that would be expected value of alpha squared EB by N naught, that would be equal to expected value of alpha squared, because that's the part that is random, times EB by N naught. And if I have done my scaling such that my Rayleigh statistics has got a unit variance, basically the real part and imaginary part have got appropriate variances. So 2 sigma squared equal to 1, expected value of alpha squared will be equal to 2 sigma squared, then this would be equal to EB by N naught. So the average SNR, you can talk about an instantaneous SNR in a fading channel, you can talk about an average SNR in a fading channel, and the case that we would like to be able to compare is when the SNR in a fading channel, in a AWGN channel, and the average SNR in a fading channel are the same, because then you can make a fair comparison between the two of them. So this is the starting point for our discussion of analytical expressions for BER. We will move fairly rapidly through the next section, but again if there is anything that is not clear, please feel free to ask and clarify yourself. So the probability of error in AWGN. So let us take for example the modulation as BPSK. That will be our reference modulation until we specify that there is a change. So probability of error of BPSK in a fading channel, Q function root of 2 EB by N naught. Again something that we are familiar with from our earlier studies. Okay. Now by the same token, if I were to look at differential BPSK, probability of error of dBPSK, this is something that you may have studied, it will be half e power minus EB by N naught. Okay, again this is material that is from books like Proakis. Okay, EB by N naught. So your instantaneous SNR or the SNR in an AWGN channel determines the performance in a. Now, if I move from here to a fading channel, and I'm going to use the term Rayleigh fading as my environment. And what I mean by Rayleigh fading is that it is a fading channel in which the real part and the imaginary part are complex Gaussian distributed, zero mean with a certain variance, and the envelope is Rayleigh distributed. So again, I use the term Rayleigh fading, but I mean a very specific environment where the envelope of the signal, received signal, has a Rayleigh statistic. So again, interpret Rayleigh fading, I just use the word Rayleigh fading, but interpret it in the correct statistical context. So if I want to ask you for the error probability of BPSK in fading, we have already mentioned, I must tell you what the alpha is, the instantaneous value of the SNR is. So this will be Q of alpha root 2EB by N naught. Okay. Now, I just want to introduce the notation that we are going to be using, and basically if we introduce the notation that the SNR is equal to alpha squared EB by N naught. Now, what would be the expression for the error function, BER, instantaneous value? Root 2 gamma. So basically the expression's instantaneous value is given by this. Correspondingly, probability of error of dBPSK in a fading channel is given by half e power minus gamma. That would be my expression that we would have to work with. So if I were to say, okay, now give me the general expression for fading. So this is something that we have already written down earlier, but let's just for completeness write down. So probability of error of BPSK in fading, have to remove the dependence on alpha. So this will be integral 0 to infinity. Alpha is the amplitude of the envelope, can go from 0 to infinity. Q of alpha root 2EB by N naught times, now I have to multiply by the PDF of alpha by sigma squared, because the Rayleigh distribution, e power minus alpha squared by 2 sigma squared d alpha. Okay. Now keep in mind that this sigma refers to the real and imaginary part of the fading coefficient, of the fading channel coefficient, and individually they are both identical zero mean Gaussians. So fading channel coefficient. Okay. So so that's the expression that we have. Now I would have to write down the expression for Q, because I cannot integrate Q directly. So Q of x is, as you know, integral from x to infinity e power minus y squared by 2 dy. Okay, so it actually becomes a double integral. Just please substitute for Q in that expression. So it becomes a double integral. The question is, does a closed form expression exist? Closed form expression exists. If so, how do we get it, and what is the methods? Usually when closed form expressions do not exist, you can do numerical, always that is an option. You can do numerical integration. Closed form expression actually does exist, but whenever you come across the integral, you don't know a priori whether the integral exists. But most importantly, out of all this, I must get insight. no point getting some complex integral and feeling very good, your ego feels very happy that you have solved a very complex integral. But at the end of the day, if you don't have intuition, there is really not much benefit from that. Okay, so the observation that we can make from here is that this double integral actually does not lend itself very easily for the unless you do some clever substitutions, which we'll sort of take you through that in one of the assignments. But now, as far as the class is concerned, I would like to take a very clever and intuitive approach which gives us a lot of insight. So let me define, rather than looking at the PDF, previously we were looking at PDF of alpha. Alpha is the envelope of the Rayleigh faded signal. So instead of doing the alpha or PDF of alpha, I want you to look at the PDF of the instantaneous SNR. Instantaneous SNR will be alpha squared EB by N naught. So if I denote this as gamma, now I want to find out the PDF of gamma, the distribution of gamma. So this is where we come across this problem, which will be very familiar to you. V is equal to square root of x squared plus y squared. Then where x and y are 0 mean, IID Gaussian, then we get the fact that V is Rayleigh distributed. This is well known. Okay. Now what happens if I have V squared is equal to square root of x squared plus y squared, okay, or sorry, not V squared. V is equal to square root of x squared plus y squared. Now this is a chi-square distribution. Chi-square distribution with 2 degrees of freedom. 2 degrees of freedom, again the statistics and all of that you would have probably have studied when you looked at transformation of variables. So here is the goal that we want to obtain. Want to obtain the let me not confuse you, let me call this as W. So W is equal to x squared plus y squared. Now I want to know what is the distribution of this variable. So basically x is equal to root W cosine phi, y is equal to root W sine phi. Again, this is something that you would have seen in the second quiz, first quiz. Basically we want to do the mapping of transformation of variables from x and y to W and phi, and if you go through the process, what you will get is the probability distribution of W comes out to be 1 over 2 sigma squared e power minus W by 2 sigma squared. It's actually a compact form. It does look like the exponential, but we will see it in a moment. Now if I were to write down the expected value of W, I call it as W bar. Now the expected value of W is expected value of x squared plus expected value of y squared, that is 2 sigma squared. So Fw of W is 1 by W bar e power minus W by W bar. And this is the general form of an exponential PDF, and you can verify that it's a valid PDF by integrating it from 0 to infinity. But the important element is that the SNR has got a expression that looks slightly different from the PDF of a Rayleigh distribution, but it is a form that is probably helpful for us in understanding or deriving the analytical expressions. Let's see if we can quickly apply, by the way, any questions on this? We are not looking at the PDF of alpha, but we are looking at the PDF of the instantaneous SNR, which is alpha squared. So basically I want to treat alpha squared as a random variable, so I called it as W and have derived the PDF, because this will be the form of the PDF of the instantaneous SNR. So the approach would be as follows, that rather than writing down the expression for the envelope of the signal, we will now write it in terms of the SNR of the signal. So let's take dBPSK as a case study. The probability of error of dBPSK in an AWGN channel is half e power minus gamma, right? I think that's what we had derived. So now we want to write down the probability of error in fading. So this is for a given value of gamma. I can tell you that this is the probability of error. So probability of error of differential BPSK in a fading channel will mean that I have to integrate over the range of alphas using the PDF of gammas using the so this would be integral 0 to infinity half e power minus gamma. So this, if you remember, is the PDF of gamma. I'm going to write down the PDF of gamma. PDF of gamma is 1 by, let me just, I need to introduce one more notation. Expected value of gamma, I'm going to use the uppercase gamma as my. So my PDF is 1 by gamma e power minus gamma by gamma d gamma. Okay, so this is the BER portion. This is the BER portion, this is the PDF portion, and I do the integral to get the expression in a fading channel. So I would like to now combine these two terms, 1/2 integral 0 to infinity, the gamma can be taken out, that's a constant, e power minus gamma into 1 plus 1 by gamma d gamma. Okay. Keep in mind that 1 plus 1 by gamma is a constant. So therefore, it's of the form e power ax, very easy for us to integrate. Please do the integration. I'll just write down 1 by 2 gamma e power minus gamma 1 plus 1 by gamma divided by the constant, which is minus 1 plus 1 by gamma, that's the, and this has to be evaluated from 0 to infinity, and please do confirm that you get 1 over 2 into 1 plus gamma. So the complexity of the integration has been taken out because it's just a simple exponential integral which most of us are comfortable doing the integration. So this is what is the average performance or the performance of dBPSK in a fading channel. So notice that the BER basically goes as 1 over 2 into 1 plus gamma. So basically it falls in a linear fashion. So if I were to write it in a logarithmic scale, my slope will be a constant, a negative constant. So the BER plots will tell us a lot. This is the BER in AWGN, the corresponding graph in fading channel, which we have already drawn before. For the first time, we're actually showing that this is indeed the case. Okay, so the way we would write it down is the probability of error of dBPSK in a fading channel as a function of gamma, where gamma is the expected value of the instantaneous SNR e power lowercase gamma, that is equal to expected value of alpha squared times EB by N naught. This would be given by 1 over 2 into 1 plus gamma. That's the net result. This is the gamma is the average SNR. The lowercase gamma is the instantaneous SNR. Okay, so that is the derivation of the PDF of the SNR and an application in terms of computing the probability of error of dBPSK. Basically, this lecture and the material that we're going to be covering in the subsequent few minutes also does involve integration. I would definitely encourage you to write it down and try out the integral. These are simple integrals, but I would always give you the hints as to be able to solve that. Okay, if you are comfortable with that, I believe we should move on to understanding the exponential PDF. So the probability distribution of gamma is 1 by gamma e power minus gamma by gamma. This is the exponential PDF that describes the instantaneous SNR. Instantaneous SNR is the exponential PDF, and this is a very useful expression for us to keep in mind, where this uppercase gamma is expected value of gamma. Okay, so it's a very compact form. It's something that we will use quite extensively in our discussions. Okay, so now what I would like to do is address the bit error rate probability of BPSK. Having done one, other can't be too difficult, right? So obviously you should be able to try this one out. So the expression for this probability of error will be 0 to infinity. The Q function I will not write in terms of alpha, I will write it in terms of gamma, root 2 gamma, and the PDF 1 by gamma e power minus gamma by gamma d gamma. It looks a little bit easier than the PDF of using the Rayleigh PDF. Okay, let's do the steps. Let me just indicate and then complete the discussion. So this you would have to rewrite using the integration by parts. Okay, the hint is integration by parts. So which says that this can be written as 0 to infinity Q of root 2 gamma d of minus e power minus gamma by gamma. Okay, so basically if you write it in the UDV form, you know how to do the distribution, the integration by parts. The integration by parts gives UV as the first term, Q of root 2 gamma minus e power minus gamma by gamma, that is U and V, evaluated at 0 and infinity, the limits, minus integral of V du, and when you work out the signs, this minus sign with the minus sign coming out, basically the second term becomes integral 0 to infinity e power minus gamma by gamma derivative of Q, basically U dV, root of 2 gamma. Okay, so basically I just rewrote the integral that we have in the form of integration by parts. I hope you will not find it difficult to evaluate and confirm that this value comes out to be 1/2. Now, second term is a little bit tricky because you have to differentiate an integral. Q is actually, the Q function is an integral, and you are differentiating with respect to what? You are respecting, this is a differentiation with respect to gamma. Differentiating with respect to gamma. So you are differentiating the integral with respect to gamma. Okay. Again, this is something that we don't encounter too frequently, but it is an important result that we should know how to differentiate an integral. If I differentiate an integral, it can be the variable on which is present in the lower limit of the integral, in this case psi of a some function, or it can be a variable that is present in the upper limit of the integral, or it can be in the integrand itself. Okay, my integral, just forget about the d by dA, is an integral of the function f between the limits psi of a and phi of a. Now I am differentiating with respect to a variable. This variable can be present in the lower limit, upper limit, or in the integrand, or in all three, or in any combination of these. So this is given by the function evaluated at the upper limit with the value phi a of a d phi a of a. Okay, that's if the variable is present in the upper limit, this term would be present. If the variable is present in the lower limit, it would be the integrand evaluated at the lower limit, psi of a comma a d psi of a by dA, this term would be present. If it is present neither in the upper limit or in the lower limit, it is present in the integrand, then you have the third term, the limits are the same, psi of a, phi of a. You would now have to differentiate the integrand d by dA f of x comma a dA. Okay. Now, do not forget that these first two terms also exist if your variable of integration is present either in upper limit or lower limit. Do not just jump in and integrate with respect to the integrand and say you are done. Now, we are differentiating d by d gamma of q of root 2 gamma. Where all is the gamma present? Is it present in the lower limit? Q function? Yes. The argument of the q function will be present in the integral. Okay. So, gamma is present in the lower, so this term will be present. Upper limit is infinity, so this is not there, and the integrand is e power minus x. Basically, it is a Gaussian. So, only the variable of integration is present in the integrand. So, therefore, this is also not there. So, we just need to evaluate the middle term. So, I hope you will be able to evaluate the middle term and then come back to tell us that the integration that we have to do basically gives us the following expression. I'll pick it up from here, but please do derive that the expression that you should get when you do the middle term will be equal to, there is a 1/2 already present. Okay. So, so it will be 1 by 2 root pi integral 0 to infinity e power minus gamma into 1 plus 1 by gamma divided by square root of gamma d gamma, and I believe there is a 1/2 up front, and that is equal to plus. Okay. So, please just make sure you make an attempt to get to this point, and it is not difficult, but just want to make sure that you are doing it in a systematic manner, and then we will pick it up from here, and actually it comes out to be minus. Okay. We will pick it up from here because this is an integral that you may be able to solve. If you are able to solve, very good. If you are not able to solve, it is just one step through a substitution. We will show you how to do that in the next class. Thank you very much.